this constant, so let's write it here, it's 1 plus k over lambda minus 1 over lambda demi-contractive. This is in line with what I said, that any average of demi-contractive map is also demi-contractive, but this constant we can show is less than k, so we can get better demi-contractive mappings. But the most important lemma for our proof is this one. So this embedding of demi-contractive mappings into the class of quasi-non-expansive is based on this lemma that I proved in this paper. We have a Hilbert space, C is closed and convex, and if T is K demi-contractive, then each average T lambda is quasi-non-expansive, so not for all lambda, but just for lambda in this interval. But this interval is just enough for us to work. So what happens? We start from demi-contractive mapping U. We find that it is K demi-contractive. We need this constant. Then we know that for any lambda, T lambda goes here, and we just use this theorem with T lambda instead of T, and we have a new result. We have a more general result for the larger class of mappings. I did this for some classes of mappings. So this is the last conclusion, that we can learn and value a failure, and this is the way we exploited this failure when we realized that demi-contractive mappings are a class of saturated mappings, so we cannot improve. This is the way we can establish lot of results. I did myself and some of my collaborators many results, and this lemma is proved in this paper, recent paper, on a useful lemma that relates quasi-non-expansive and demi-contractive mappings. In the previous paper I mentioned here, in that one I just mentioned this lemma. I stated, but the proof, the whole proof, and all implications of this result are included in this paper, and this paper is also containing this diagram I presented you at the beginning. So now, it is important to tell you that the same happens with the class of strictly pseudo-contractive mappings space. Why? Because it is the class of enriched non-expansive mappings, so any convergence theorem for Krasnoselski-Mann iteration, there are iterations I'll mention in my next talk. There are iterations like Halpern, which cannot be used in this way. And for Krasnoselski-Mann type iterations, we can transport any result for non-expansive, from the class of non-expansive mappings to the class of strictly pseudo-contractive mappings. This has been done by Browder and Petrichin first, but they did in a very, how to say, hidden way. So they did not say nothing clear. So they just used this fact. If T is K strictly pseudocontractive, translating what they did, because they did not explain it this way. If T is a K strictly pseudocontractive mapping, then the average map T lambda is non-expansive for this, the same values of K. And Petrichin, in this nice paper, it was a paper presented at the summer school in 1968. They published their paper in 66, and this was published in a book edited by, it's from Italian, something with summer school in ISPRA. This was re-edited by Springer in 2011. Very nice book. And if someone here, Petrichin is more explicit in showing that this happens. And they used, but no many mathematicians noted this. The ones who noted this is this Zhou. In 2008, he used this lemma, this property, to prove convergent theorems for fixed point iterative schemes in the class of strict pseudocontractions for single valued, and then he did the same for larger, for a more particular, a larger class of spaces, two uniformly smooth Banach spaces, very similar results, but by using this lemma. Again, this is similar to the lemma I presented for demi-contractive. So, as I mentioned, they knew this technique of enriching, but it was not explicitly mentioned in their paper. They just, this was the way mathematicians were working 50, 60, 70 years ago. By the way, I don't know if you know, this is this prestigious journal, Combrome de l'Académie de Sciences Paris. If you look to this journal, you will see that the papers are without proofs. So just the results. Very interesting way. They don't include proofs, so they just put the paper, the results. Of course, when submitting the paper, the authors are including the proofs because the reviewers are checking the results, but they do not publish. So in that period, this was the way to publish mathematics, and this reminds me, I don't know if you know this name, Cardan. It is related to solving the equation, third degree equation, which can be reduced to this. So at that time, this was 15th century. So this was the period, 50th, 60th century. How were doing mathematicians? So there were a kind of public competitions. And I was a mathematician, I said, I can solve any equation of third degree. So just put me. They did not say the rule, the formula. They did not say. It is said that Cardano himself has paid money to someone else to know this formula. And at that time, this was the way. So you can earn money, and it was a competition. How can you solve this? And the classification, the ranking of mathematicians of that time was about how they know or not to solve some problems. But this comes from antiquity. This comes from antiquity. I don't know if you, there is a very nice problem by, how is this, his name? I have now lapsus. It's a antique mathematician. Sorry, I don't remember. But he put a problem 300 years before Jesus Christ, years of 0, and it has been solved after almost 2,000 years. It was. It's about number of cows in an area, and he put this was the style. So in order to show one mathematician is better than the other, he put a problem. So this is my problem. Solve it. If you are solving it, you are better than me. If you're not, and this problem, I remember the name of this famous mathematician who did this. Coming back to our topic to close this session, this was the story with 4 classes of mappings. So let's remind them. Quasi, non-expansive, they are paired, demi-contractive. In the sense that this is the enriched class of non-expansive, quasi non-expansive, and non-expansive with strictly pseudo-contractive. These are saturated and these are unsaturated classes of mappings. There are a lot of other non-expansive type mappings, and here are a few of them. Firmly non-expansive, lambda firmly, asymptotically, strongly non-expansive, Suzuki non-expansive, Suzuki generalized, alpha non-expansive, non-expansive type mapping, generalized, and so on. Among them, enriched non-expansive, enriched quasi non-expansive, I mentioned, enriched strictly, which is not. So the challenge for you is to check this list and try to show, is this saturated or not? Is this saturated or not? And so on. This is a topic to think about, and this would, because these 2 classes of mappings are extremely important in applications. Signal processing, image processing, data science, and so on. Very important, because they are coming naturally from external problems, let's say from real world problems. And but the others are also these classes of mappings, which are, let's say, theoretical, are also important. So the challenge is this one. Try to see what kind of mappings. Here I present at the end this diagram. I found it after I published my own diagram, but this you can see it's also referring to non-expansive mappings. So here are non-expansive mappings. Here are contractions, and it's very nice put. The contractions are here, very small class of mappings. Then you can see firmly non-expansive mappings are important because they are resolvents of some operators. And also metric projections, which is, I'll show it's important in building gradient and projection type algorithm, is again very important. The fact that all are non-expansive is important because we know for non-expensive mappings that composition of non-expensive mappings is also non-expensive. So this is important because we will see next that we have composition of projections. So this is important that we know they are still non-expensive. And lambda non-expensive mappings are here, and not to forget about strongly non-expensive mappings, which in a uniformly convex space are including all these classes and is included in the class of non-expensive mappings. This is a nice paper dealing with the importance of firmly non-expensive mappings in applications. So, to conclude, let's remind the main ideas in this lecture. In Hilbert spaces, any convergence result for demi-contractive mappings can be derived from the corresponding one in the class of quasi-non-expensive. This was the case for Hicks and Kubitschek in the case of getting the class of demi-contractive mappings, and similarly the same statement for the class of strictly pseudo-contractive mappings. Any convergence result here should be for Krasnoselski-Mann iteration can be derived from the corresponding result in the class of non-expensive. And here I selected some in MathSciNet. The information is from MathSciNet. So this is the number of papers having in the title the word non-expensive and fixed point, related to fixed points, this number, big number. This is the number of papers having strictly pseudo-contractive mappings, and the others one. What does it mean, this? Only a few results for non-expensive mappings were transported to strictly pseudo-contractive mappings. It's room for work. And only a few, so 1/5 of the papers for quasi-non-expensive were, let's say, in some way transposed to demi-contractive. Again, it is room for work here to see what can I do. Now, the problem approached by Chidume. So the problem is now, and it is a very interesting problem, we worked in Hilbert spaces. All were done in Hilbert spaces, what I presented here. But in Banach spaces, we have the concept of non-expansive, of strictly pseudo-contractive, of quasi-non-expansive, and of demi-contractive. What is the situation and what is the relation between these classes? One PhD student of mine, one former PhD student from Thailand, he did very nice, nice discussions, not in Banach spaces, but he worked in these Kate zero metric spaces, and very interesting. He needed to, the class of strictly the class of demi-contractive mappings is not transposed trivially to such spaces. He needed to introduce a new definition for demi-contractive adapted to this setting, and he succeeded to show that in this setting, with some assumptions, with some additional assumptions, the class of demi-contractive mappings is the enriched class of quasi-non-expansive, and some others. So he was very successful. I'm not, if I'm not wrong, he published 8 or 9 papers for his PhD thesis. When he finished his PhD thesis last year, he had this number. Incredible. He was working very hard. He visited me for 3 months at my home university, and he worked a lot. Very, very nice person from Nigeria too, but he did his PhD in Thailand, in KMUTT, where is Phum Kumam, under the supervision, co-supervision of Phum Kumam and myself. And so there are ways to continue this work also in this kind of settings. And that's all for today. It's time for questions, if you have.
Yeah. Many thanks, Professor Virendra.
Sorry.
On this iteration side, I think a lot of results Professor discussed, recent results also, and a lot of motivational mathematicians, how they are working, their philosophy to work on. And there are a lot of things that we miss mostly, and we presume that the concepts may be similar, or we like writing the properties of Banach space and writing the properties of mod and metric spaces. We feel they are more or less same, but actually they are not same. Their geometry is different, their structure is different. So feeling and expressing and understanding, these are the 3 ways to understand such things, and he very nicely explained all such things. If you have any question, you can ask this. Yeah, please.
1 second. I would like to remark on the order of convergence of all these iterations.
My last lecture
Yes.
will be. So, for the beginning, I can say the following, to repeat what I said at the beginning. Fixed point iteration algorithms are linear, have linear convergence, so are very slow in general, are slow, and I'll show you a few things about this. It is possible to accelerate some of them. And I had one of my PhD students, some 10 years ago or more, she did some work on accelerating fixed point iteration methods, because they are generally slow. By the way, because it's a very good question, thank you. By the way, I have a paper. I hope tomorrow I have a meeting, so it will be crazy, but I'll try to collect some papers from the last 10 years, let's say. I published a paper where I shown that most of these inertial algorithms are very slow, are really slow. And you will not believe this Krasnoselski-Man, simple Krasnoselski-Man, is better than very elaborated algorithms. They are strongly convergent, but in practice they are very slow, very slow. What does mean very slow? We'll see when I present error analysis for iterative methods. This means if we perform 10 iterations to get a good approximation, this is very nice. But if we need 10,000 iterations, the errors will accumulate, and the risk is that the solution will be aside the true solution. So maybe I have time to put some material for Friday, because this will be Friday when I'll speak about error analysis, and this is the point. So there are algorithms that are, have rate of convergence 2 Newton, for example, but you know, when you have an advantage, you have one or two disadvantages. Newton is convergent with rate equal 2, but it needs the the starting point to be close to the solution. How to know where is the solution if you are searching for solution. So, but if we start with an initial value far away from the solution, the Newton method will go far away from the solution. But it doubles the precision each step. So this means, so we get, it is faster than any iterative method. I'll show you some of these facts, okay? Good question. So any fixed point iterative method is typically linear or has linear order of convergence. This means it's very slow. Let's say not very slow, but slow. It's slowly convergent.
Monotonically decreasing.
Yeah.
Yeah. So you have seen one table also professor has shown in which the values of the lambda and then the convergence when actually the iterations, no? You have seen some iterations they are putting lambda value as 1 after 5 iterations, few iterations after 35 also. So this is what the rate, you are talking about the sequence, but when you are iterating such things by using the MATLAB or Mathematica, so you realize all such things. So it's fine, but what I feel is like non-expensive mapping, I also came across with several contractions where I find lot of difficulty in showing the sequences convergence part, especially whether looks like is fine, but whether the sequence converges or not, difficult to analyze. We published by again putting some extra conditions, because without using the computer and without, because just one numerical example is not enough.
Yes.
When you talk about the for all x, then how you can be very particular about a particular value. And sometimes what happens, even you pick the initial and terminal points, it is fine, but in between points possibly is not working. That is possible. So there are good number of cases, but since this generation is a computer-oriented generation and they are very fast in learning the computers, computer programming, okay. So I think like Professor said, you can do well, you develop some algorithm and you try what to do if such kind of machine can be developed, and why not a virtual kind of simulation can be conducted on such machines to analyze the rate of convergence of the iterations. That is possible. So if no questions, then thank you. Tea time. Tea is ready.
Thank you.
Now not a photograph, because they have removed the banner. One program is going on in the hall, so they will fix the banner at 1 o'clock. At the lunch time only we have the chance, if possible. Otherwise tomorrow we will. Okay.